Video 1, Theory 1, week number 14, unit on magnetism. I just want to start off with talking about some definitions so we understand some of the terms. So the first one I want to talk about is permeability. And permeability is known as a measure of a material's ability to become magnetized. So some materials are permeable and some are less permeable. The next one here is reluctance. And reluctance is the resistance to magnetism. So soft iron has a very high permeability but a low reluctance. So reluctance is like resistance, but in magnetism we don't call it resistance, it's called reluctance. It is more reluctant to become magnetized. Then we get to saturation. And saturation occurs when all of the molecules of the magnetic material are lined up. And it's similar to, as my example here, is to pouring 5 liters of water into a 5-liter bucket. It simply cannot hold any more. To get more water, one would require a larger bucket. For a stronger magnet, one would need greater surface area. So saturation is when all of the molecules are lined up. Then we get to residual magnetism. Now, this is the amount of magnetism that remains in a material after this magnetizing force has been removed. So that's residual magnetism. Then we get to magnetism and electromagnetism. So there's 2 primary categories of magnets. The first one is a permanent magnet. And now permanent magnets retain their magnetism for very long periods of time. They will lose their magnetic properties, however, if heated. Now, iron loses it around 750. I think it's 770 degrees to be more accurate, but nonetheless. So when you heat it up, what ends up happening is that those molecules are no longer lined up. They start vibrating and shifting around, and when the heat is taken away from it, then they resettle back in their natural state, so they're no longer lined up. So slammed, beaten, or pounded. So you can take like a magnet, and if you slam it on the ground, or if you hit it really hard with something, then you can demagnetize it. And of course, that's because what you're doing is you're realigning it at a molecular level. So those molecules are no longer lined up. When they're lined up, we have a magnet. When they're not lined up, we don't have a magnet. The other way is to place it in a magnetic field and then slowly reduce that amount of magnetic field. So we pull it out of the magnetic field or reduce the magnetic field variance. So examples for permanent magnets, lodestones, alnico 5 magnets, which are, they call the magnets that you go out and you buy, semi-precious type materials. Alnico 5 is actually, there's actually 5 metals in there, but alnico stands for the aluminum, nickel, and cobalt that they use for those. And you get very strong magnets out of those. Then the other category of magnets is temporary magnets. So those that lose their magnetic properties quicker after the magnetizing forces have been removed. So you can imagine that you've probably seen, if you buy a new fridge or when you move, perhaps there's fridge magnets that have fallen in behind the fridge or down at the bottom. It's because over time they actually lose their magnetic properties. And then we get to electromagnetism. Now, this picture here is Michael Faraday. And he determined that when a permanent magnet is moved in the vicinity of a conductor, it will induce a current in the wire. So that is called electromagnetism, or induction, rather. So the next thing I want to talk about is flux. And you've probably heard this before. We're not talking about the DeLorean and the flux capacitor. What we're talking about is flux. And flux is the invisible lines of force that surround a magnet. You've probably seen this before. If we have a north and a south magnet. This is a magnet. So if we have a north and a south pole magnet, what ends up happening is you get these magnetic lines of flux. And these magnetic lines of flux sort of come out like this, and you've probably seen this before. You can do this at home too. If you take a magnet and you put it under a piece of paper and then sprinkle iron filings on it, you'll see these magnetic lines of flux start to appear. And the magnetic lines of flux, even though I showed it there, they don't cross. And they come out of the North Pole and they go to the South Pole, and they're unbroken loops is flux. And they're sometimes just called invisible lines of force. And if you look at here, you can see that there is a value of density which is greatest at the poles. So if I take a look at this, I look at just a snapshot of that area there, and then the same area like here, we can see in terms of like its density, it's very dense at a pole and not so dense outside the pole. Getting back to the flux, the way it runs is that the flux runs from the North Pole of the magnet in this direction to the South Pole of the magnet, and then from inside the magnet from the south to the north. So flux runs from the north to the south, like that. The symbol for flux is the Greek letter phi, and the import when I did this didn't work, and the Greek letter phi looks like this. You'll have to see it look like that, and that represents flux. The flux lines at the north pole of the magnet re-enter the South Pole. Flux travels from north to south outside the magnet and south to north inside the magnet. So therefore flux density is greatest at the poles. Now the flux lines will not just take that standard shape. The flux lines that the path takes will be a function of where the flux lines can most easily set up in. So it would have to do with the permeability of the material and the reluctance of the material. So a magnet will induce a magnetic property in a nearby material if the object is in the path of the flux line and the material is permeable with a low reluctance. So this is called induced magnetism. So if we look here, I've got so same thing, I'll use my north and my south magnet here. And I have just a piece of, I'm going to say this is just a piece of soft iron, and I've got it within this magnetic field. And if we look at our flux lines, what's is going to end up happening is these flux lines are going to come out here, and they're going to go up like this to the material like this, and then it's going to go through the material here like this, inducing a magnetic property in this piece of metal, and back out again to the magnet, and it creates this loop, and these loops, and we've got these flux lines. So we've got all these flux that start setting up within this material here, and as a result of that, what's going to end up happening is that this pole here, this piece of material is going to become a temporary magnet, and it's going to have this magnetism induced into it. And notice that this is the South Pole because the magnet flux runs from north to south, and this will be the North Pole, and you can see that, well, it's running from north to south back to here again. So these flux lines will continue, and as a result, this material here will become magnetized. And with how much residual magnetism there is, that would be determined by the permeability and the reluctance of the material. So when this magnetizing force over here, we call the force magnetic, is removed, then we will still have some residual magnetism in here. But notice that the polarity of the induced magnetic property places the unlike poles adjacent to each other. So if you see north and south, north and south. The last thing I want to mention in this first video is we're talking about the amount of flux. And the amount of flux we know is the Greek letter phi, and it's equal to 1 Weber. 1 Weber is 100 million lines of flux